I'm going to continue on the example that we've been doing on last lecture. So I'm going to continue on example longitudinal shear. But a quick reminder regarding term test 2, it will be on July 11 from 7 p.m. to 9:30 p.m. The topics to be tested are from homework 4, 5, 6, and from the lectures. Okay, so the questions can come out from homework 4, 5, 6, and all the examples in the lectures. And the location, I've not booked a room yet, but I will announce it once I know the location or once I've booked the room. So we are going to continue on this example that we started on Tuesday, okay, on longitudinal. And the term test is up to longitudinal shear, so it's up to this topic. When I teach next week on Tuesday, that topic will not be considered in your term test, okay? So we're going to continue on example. So just to very quickly recap on this problem. So the objective is to determine the value of P, which is the load at a simply supported structure. So what you have over here, the diagram on the I think I should rearrange the diagram. Usually we view it this way. Okay. So if I were to draw the transformation, this is X, Y, and we have rotation about Z. This is the cross-sectional view. And you have Y, Z, and you have rotation about X. Okay. So over here, we know that it's a Vy. Okay. And we do know about the failure modes, right? There are 3 different failure modes, but what's given to us is we are given to us values of normal stress due to bending, shearing stress due to the shear force, and the fastener. Okay, the properties of the fasteners that's given to us. So on Tuesday we have done mode 1, which is failure due to the fastener. So just to quickly recap, the shear flow Q is equal to resistance force of the fastener and then we divide by spacing. So we know that this will be equal to 600 divided by a spacing 6. We multiply by 2 over here because it's double shear. Given to us, the 600 is a single shear, double shear. You multiply by 2 because you have 2 surface area over here. So it's a double shear configuration. So we have this as 200 pounds per inch. And we also know that Q can be related to VQ over I, right? And we also have found out that or given I did not determine I because second moment of area is really straightforward to determine. So I is equal to 2902. And then Q, just to quickly recap, there are two new rules that introduced is the shear force will distribute in the member first. Okay, then from the member, it would the fastener would transmit the shear force. So the first moment of area is to be taken on the entire block. Okay, not above the fastener or below the fastener, no, the entire block first. Okay, so we know that QZ is equal to width is 6, depth is 4, the Y bar is 10, but not 10, sorry, 5 passed by 2, because if this is the geometric centroid, right, this is 5 and 2, so this will be equal to, so this is an inches to power 4, so it's 5 plus 2 times 6 times 4, it's going to 168, right? So we know our QZ, I given, now we also have a relationship where V is equal to P over 2. Right? We drew the shear force diagram. So when we sketch out the shear force diagram, just to quickly recap, this is our V, and this is our X. We have a diagram looking like this. And we know that this is V over 2. Over here is minus V over 2. So from here, we know that we have 200 is equal to P over 2 multiplied by 168 divided by 2902. So from here, the load due to the fastener is equal to 6909 or 6910. I mean, we're at 200 times 2902 divided by 168 times 2. Yep, 6910 pounds of force. Okay, and this is due to mode 1 failure. So, i.e., the fastener. Okay, I bear with me a bit. I need to make some adjustment to my display. Right, so we have completed mode 1 due to the fastener. The next thing we are going to look at, okay, so given to us, if you look at the question, they say the shear force or the shear stress allowable in the wood is 3 KSI. Okay, so we're going to look at mode 2. So mode 2 is shear failure. Due to the wood. Oh, yeah, which failure. Sorry, failure due to the wood. Okay, so for this case, we can use the term shear stress, or we have to, first of all, we have to determine the location of tau max. Okay, and we know that tau max is equal to V over I are constant, right? So the trick about getting tau max is we have to find the location where Q is max divided by T, that is the minimum, right? Q is the max, T is minimum. So when you take this diagram, the cross-sectional view, I'm going to sketch out the position of the centroid. So we are aware that this is the centroid. Right? So we know that, and I'm going to call this position C, right? So we realize at point C, right, Q is max and T is also at its minimum. So we know that the maximum shear Can you hear me? Check. Testing, testing. Yeah, you all seem to be able to hear me. You all can see my screen, right?
Yeah,
Yeah,
you're back.
yeah, I know. There was something weird. Okay, I hope was not for too long. So just to quickly recap, we are going to mode 2, and at point C is where we have Q max and T mean. So from here, you can use either uh, you can use either uh, thin wall analysis or non-thin wall analysis. I believe the answer will be the same. So let's use non-thin wall analysis. Okay, non-thin wall analysis. Okay, so we don't design the shear flow. Okay, we only know the thickness, right, at point C. So we're going to go through Q max or Q about Z at max. So this will be the Q of the flange plus by Q of the webs. So we have width is equal to 6 for the flange. The depth is 4. The Y bar is 5 plus 2 will be 7. And then the web, you have left and right, which is the 2 over here. The thickness is 0.5. The thickness is 0.5, and then you have the what? That's the width. The depth is 5 plus 2 plus 2. 5 plus 2 plus 2 is 9. And then you have the Y bar 9 divided by 2. Okay. So this will be equal to 6 times 4 times 7, 168, plus by 2 times 0.5 times 9 over 2 is equal to 40.5. So 166 plus 540.5 is equal to 208.5.